Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine taking Mount Everest.
Right. Okay, I'm picturing it.
You take the entire mountain, you put it in this massive cosmic vise, and you just crush it down until the whole thing fits inside a single sugar cube.
Wow.
Yeah. And then take two of those impossibly dense sugar cubes, put them out in deep space, and make them spin around each other at like 40% the speed of light.
That is, it's just a terrifying amount of energy.
Exactly. It's completely wild. And today, we are looking at a monumental breakthrough in theoretical physics. This was published on February 18th, 2026 in Physical Review Letters. And it basically finally lets us hear exactly what is happening inside those spinning objects.
Which is something we've been trying to do for a very long time.
A really long time. So, okay, let's unpack this, because to truly grasp the sheer scale of this discovery, we have to look at a realm where the laws of physics, like the rules that govern the reality you and I experience every single day, are pushed to their absolute breaking point. We are talking about neutron stars, objects so dense that their gravity is second only to a black hole. And for decades, what actually exists inside the core of these stars has been one of the most stubborn mysteries in modern astrophysics.
It really is a profound mystery.
Yeah.
And to understand why it's so stubborn, we should probably look at how a massive star actually dies.
Yeah, let's set the stage there.
So for millions of years, a star is locked in this delicate, kind of epic balancing act. You have gravity constantly trying to crush the star inward, right? Pulling all that unbelievable mass toward the center.
Just a constant inward squeeze.
Exactly. But the nuclear fusion happening in the star's core pushes outward. It creates this immense thermal pressure that essentially holds gravity at bay. It is a stalemate.
Right, but the star can't burn forever.
No, it can't. Eventually, the star simply runs out of fuel. The fusion stops. And the moment that outward pressure vanishes, gravity finally wins. In a fraction of a second, the core collapses in on itself, blowing the outer layers away in a massive supernova.
Which is just an unimaginably violent explosion.
Oh, incredibly violent. And what is left behind in the center is the collapsed core, the neutron star.
And that collapse is where things get truly wild, right? Because when we say gravity wins, we mean it crushes the matter so forcefully that it overcomes the fundamental structures of atoms themselves.
Yes, it absolutely breaks them.
Because usually atoms are overwhelmingly just empty space. You have a tiny, dense nucleus of protons and neutrons in the middle,
Right.
And it's surrounded by a massive buzzing cloud of electrons. And there is a strict rule in quantum mechanics, the Pauli exclusion principle.
Ah, yes, the exclusion principle.
Yeah, which basically says certain particles, like electrons, absolutely refuse to occupy the same quantum state in the same place. They push back against being squeezed.
It's called electron degeneracy pressure. It's a fundamental resistance built into the fabric of matter.
But the gravitational weight of a collapsing stellar core is so overpowering that it just shatters that resistance. It literally forces the electrons to crash into the protons.
It overcomes the quantum rules, essentially.
Yeah, exactly. And when you squeeze an electron and a proton together under that kind of intense pressure, they fuse. They undergo what's called inverse beta decay, and they become a neutron.
Right.
So you end up with an entire star that is essentially one gigantic, city-sized atomic nucleus.
Think about the scale of that for a second. The empty space within the atoms, the space that makes up almost everything we know, is completely eradicated.
It's gone.
Gone. You're left with a sphere maybe 10 to 15 miles across, so basically the size of a sprawling city. But it contains more mass than our entire sun.
It's hard to even wrap your head around that level of density.
It really is. However, calling it just a giant ball of neutrons is actually a massive oversimplification.
Oh, really?
Yeah, we understand the outer crust reasonably well, and it's
Uh-huh.
likely a rigid lattice of iron nuclei. But as you travel deeper into the star, the density crosses a threshold known as supernuclear density.
Supernuclear density.
Right. This is where matter is packed more tightly than it is inside the nucleus of a single atom.
Yeah.
And as you plunge into the core, the physics becomes incredibly strange. We strongly suspect it is not just a uniform sea of neutrons down there.
So what else is in there?
Well, there are likely heavy elements, free electrons, and free protons all mixed in.
Plus, we are dealing with quantum mechanics operating on a macroscopic city-wide scale now, right?
Exactly.
Because deep within the star, the conditions might actually trigger quantum superfluidity and superconductivity.
Yes, which are fascinating states of matter.
I mean, we are talking about a fluid that flows with absolutely zero friction. If you stirred a cup of this superfluid inside a neutron star, it would theoretically keep spinning forever. It would never slow down.
Never.
And a superconductor conducts electricity with zero resistance. Those phases of matter are mind-bending enough, but they aren't even the ultimate prize here, are they?
No, they are not.
The holy grail of neutron star physics lies at the absolute dead center, the inner core. Because at those unfathomable pressures, the math suggests that even neutrons themselves cannot survive intact.
And that brings us to the fundamental building blocks of matter. Neutrons and protons are not the smallest things in the universe. They are made of elementary particles called quarks.
Quarks, right.
And these quarks are bound tightly together by other particles called gluons. The strong nuclear force is what keeps them locked up tight inside the proton or neutron.
So they're basically inseparable under normal conditions.
Exactly. But at the very center of a neutron star, the pressure and density are so extreme that we believe it overwhelms even the strong nuclear force.
Okay, I have an analogy for this. Think of it like a bag of individually wrapped hard candies.
Okay, I like where this is going.
So you have this bag of candies and you leave it in a hot car. Normally, you can reach into the bag and pull out individual candies and their wrappers. Those are your individual protons and neutrons.
Right, they have distinct boundaries.
But under extreme heat and pressure, the wrappers dissolve, the candies melt together, and you are left with one giant, sticky, inseparable mass of sugar.
That is a perfect way to visualize it. That is exactly what happens to the quarks. The boundaries between individual neutrons dissolve, and you get this continuous, sloshing, highly dense state of matter called a quark-gluon plasma.
So the neutrons literally bleed into one another. They create this soup of free-floating quarks and gluons.
Yes.
And this is vital for you, the listener, to grasp. Because this specific state of matter, this ultra-dense quark-gluon plasma, does not exist anywhere else in the modern universe.
Nowhere. Absolutely nowhere else. To find it naturally occurring anywhere other than the heart of a neutron star, you actually have to rewind the clock to the very beginning of everything.
Like the Big Bang.
Exactly. You have to look at the first few microseconds after the Big Bang. In those initial fractions of a second, the entire universe was so incredibly hot and dense that all matter existed as this exact same quark-gluon plasma.
That is wild.
As the universe expanded and cooled, the quarks eventually clumped together to form the protons and neutrons that make up the reality we see today. So, by trying to understand the inner core of a neutron star, we are attempting to peer directly back into the primordial conditions of the universe.
It is like finding a perfectly preserved fossil from the dawn of time. Except this fossil is currently spinning around in deep space, encased in a sphere of impenetrable iron.
Right, which makes it incredibly difficult to study.
Yeah, but hold on. If no lab on Earth can squeeze matter this hard without vaporizing it, we are stuck. I mean, we obviously cannot send a probe into a neutron star.
Oh, absolutely not. The gravity would spaghettify the probe instantly, and the radiation would melt it before it even got within 1,000,000 miles.
So how do we examine something we can never physically touch?
If we connect this to the bigger picture, you start to see the fundamental frustration of extreme astrophysics. We do have laboratories on Earth, of course.
Like CERN, right?
Yes, we have the Large Hadron Collider at CERN. And in those colliders, we can actually create tiny, fleeting droplets of quark-gluon plasma.
Wait, we can?
We do this by smashing heavy ions together at nearly the speed of light. But here's the catch. The kinetic energy of those collisions is so violent that it generates immense heat. We are probing the plasma at extraordinarily high temperatures.
Oh, okay.
But a neutron star core operates on a completely different axis of physics. Yes, it is hot by human standards, millions of degrees, but in the context of subatomic physics, it is considered a relatively low temperature while being unbelievably dense.
Okay, so we basically have a massive blind spot in our physics maps. We can easily create high-temperature, low-density plasmas in our colliders, but we have absolutely no machine on Earth capable of creating ultra-high density at a relatively low temperature.
Exactly.
Because you can't just build a mechanical press that squeezes matter that hard without the friction heating it up to trillion-degree collider temperatures.
Which is why Professor Nicholas Younes, who is one of the key physicists behind this recent breakthrough, pointed out that the universe has graciously provided us with a natural lab.
The neutron stars themselves.
Precisely. They're the only laboratories where these specific extreme conditions exist. But historically, we have faced an enormous observational wall.
Because of how we observe space.
Right. All of traditional astronomy is based on electromagnetic radiation. Catching the light the universe emits, whether that's visible light, radio waves, X-rays, or gamma rays.
But you cannot see inside a neutron star with light.
Not at all. The outer crust is completely opaque. X-ray telescopes might read the surface temperature, and radio telescopes can track the star's rotation if it is pulsing like a pulsar. But electromagnetic observations will never penetrate the crust to show us the core.
So if light cannot pierce the surface and we cannot recreate the core on Earth, we are effectively blind.
We are.
Unless, and this is the key, unless we stop trying to look at the star and instead figure out a completely different way to observe it. If we cannot see the core, we have to listen to it. We have to listen to gravity itself.
And to understand this new method of observation, you have to imagine not just one neutron star, but two.
A binary system.
Yes, binary neutron star systems. Two incredibly dense stars caught in each other's gravitational pull, orbiting a common center of mass. Over millions of years, these two stars spiral inward, getting closer and closer together.
Like a cosmic dance that's slowly collapsing.
Exactly. And as they do, their immense accelerating mass churns up the fabric of space-time. They lose energy to the universe in the form of gravitational waves.
Which are actual ripples in space, right?
Yes. They are physical vibrations in the geometry of space itself, radiating outward at the speed of light.
It is so important to note that a gravitational wave isn't like a sound wave traveling through the air. It is the actual distance between 2 points in space physically stretching and compressing.
That's a great distinction.
And as the stars bleed energy into these waves, their orbit shrinks. But the crucial part, the window into their interiors, opens up right before they collide.
Right, because when they get close, their gravitational fields are so monstrously strong that they begin to physically tug on one another. It is the exact same principle as the moon pulling on the Earth to create ocean tides.
Only in a binary neutron star system, those tidal forces are incomprehensibly powerful. We aren't talking about water sloshing around. We are talking about the incredibly dense, rigid matter of the star itself being stretched and deformed by the gravity of its partner.
They literally bulge outward toward each other. And because they are orbiting rapidly, this gravitational pull is dynamic. It is constantly changing, squeezing, and releasing the star's material.
Just continuously kneading it.
Yes. And this dynamic squeezing excites oscillatory patterns deep within the stars. We call these patterns modes.
Okay, here is where Abhishek Hegade, the researcher who led this breakthrough, offered a really brilliant analogy. He suggested that these modes are exactly like the ringtones excited in a bell when it is struck by a hammer.
It is a phenomenal way to visualize the mechanics. The gravity of the partner star is the hammer, and the neutron star is the bell.
I love that.
When you hit a bell, the metal vibrates at very specific frequencies. And those frequencies depend entirely on what the bell is made of, its shape, and its internal density.
Right. A bell made of solid brass sounds completely different from a bell made of glass or a bell filled with water.
Exactly. As the neutron star gets squeezed and deformed, its internal matter vibrates. And because these stars are generating gravitational waves as they orbit, these internal vibrations, these specific modes, actually leave a physical imprint on the gravitational waves being emitted.
So what does this all mean? It means the internal shaking of the star slightly alters the rhythmic ripples of space-time radiating outward.
It changes the song, so to speak.
Right. If the inside of the star is made of a rigid superconducting lattice of neutrons, it will vibrate differently. It will have a different ringtone than if the inside is a sloshy, fluid-like quark gluon plasma.
That is the core idea.
So the gravitational waves washing over the Earth right now carry the physical signature of the star's core. If we can capture those waves and read that specific imprint, we can finally determine exactly what the core is made of.
That is the elegant theory. By understanding the mode frequencies of oscillation and their decay times, which is how long it takes for the vibrations to die down, we can map the internal composition of these stars. We just have to listen to the ringtone and read the math.
Read the math. But here is the brutal reality. Mathematically, proving how to read this ringtone has been an impossible wall for physicists for years.
A massive wall.
The math of the universe is not as simple as the math of a brass bell on Earth. To understand why the brightest minds were stuck, we have to look at the massive gap between classical Newtonian physics and Einstein's reality. So let's start with the baseline. How do we normally solve these kinds of vibration problems in classical physics?
Well, in a non-relativistic setting where gravity behaves the way Isaac Newton described it, as a simple force pulling across a flat, static background of space, we understand dynamic tidal responses perfectly.
Straightforward.
Very straightforward. When a Newtonian body is squeezed by tidal forces, the solutions to the mathematical equations are simple. The modes, those internal vibrations, behave exactly like damped harmonic oscillators.
Well, the spring.
Exactly like a spring.
If you pull a heavy spring and let it go, it bounces up and down, but friction eventually dampens the bouncing until it stops.
Precisely. In Newtonian gravity, you can calculate the exact frequencies at which the star will oscillate and how fast those oscillations will dampen. And here is the most critical mathematical concept for this entire breakthrough.
Okay, what is it?
In Newtonian theory, the object's entire tidal response can be expressed solely in terms of these modes. Mathematically, these modes form what is called a complete set.
A complete set. Let's break that down because it is huge.
It is everything.
It basically means that if you add up all the different vibrations, all the different overtones and fundamental frequencies, they perfectly describe 100% of the deformation happening to the star.
There are no missing pieces.
Right. There are no leftover pieces. There is no mystery motion happening that isn't captured by the math of the springs. Think of it like a recipe where all the ingredients perfectly add up to the exact weight of the final cake.
That is a great way to put it. And Professor Yunes was very explicit about why this matters. He pointed out that without a complete set of modes, your mathematical model is fundamentally broken.
You can't bake the cake.
No, because if the modes aren't complete, you are missing part of the tidal response. You are omitting crucial physics. If you try to interpret the gravitational wave data without a complete set of modes, your conclusions about the star's interior will just be entirely wrong.
So scientists globally have desperately hoped that this neat, tidy mathematical package where modes form a complete set also exists in Einstein's theory of general relativity.
Yes, because neutron stars do not live in Newton's universe. They live in Einstein's universe.
They're highly relativistic objects.
Extremely. They're incredibly dense, and in the final moments before they merge, they're whipping around each other at speeds approaching 40% the speed of light.
40%. Trying to do calculus on two city-sized objects spinning around each other at 40% the speed of light is, well, it's like trying to map the aerodynamics of a blender while you were inside it.
That is hilarious, but true. The amount of space-time distortion they are creating is incomprehensible.
It really is.
It is staggering. And the equations of general relativity are notoriously complex because they are nonlinear. Everything affects everything else in a continuous feedback loop.
Mass tells space-time how to curve, and curved space-time tells mass how to move.
Exactly. So when you have two incredibly dense stars in a binary system, severely distorting space-time, it becomes nearly impossible to mathematically separate the effects of one star from the other. The boundary conditions, the mathematical rules that allow you to solve the equations at the physical edges of the star, completely fail.
And it gets worse. Because in general relativity, gravity isn't just a force pulling across empty space. Gravity is the curvature of space-time itself. So a neutron star's extreme mass doesn't just pull on things. It radically changes the geometry of the space inside the star and the space outside the star.
In Newtonian physics, you pretend the star exists in a nice, flat, empty vacuum. But in general relativity, you have to calculate the tidal field across intensely warped spacetime, both inside and outside the object simultaneously.
Okay, but that brings us to the final, most devastating complication that prevented physicists from finding a complete set of modes for decades. We established earlier that these binary systems are spiraling inward because they are continuously losing energy to the universe in the form of gravitational waves.
Yes, they are radiating energy away.
Hey, hold on. I have to push back here.
Okay, go ahead.
You're contradicting the core setup. We just established that the entire goal is to mathematically define a complete set of modes, a perfect, closed mathematical description of the star's internal vibrations where all the energy is accounted for.
Right.
But if the entire system is constantly radiating gravitational waves, energy is actively leaving, the bucket is leaking.
That is exactly the problem.
How can you possibly have a perfectly complete, closed mathematical set if energy is continuously bleeding out into the void of space? It is like trying to calculate the exact perfect acoustics of a concert hall while the walls are actively blowing away in a hurricane.
That is the exact paradox that brought everything to a grinding halt for so long. Newtonian theory doesn't account for this loss of energy to gravitational radiation. It assumes a closed system.
But in relativistic reality, the system is bleeding energy.
And fundamentally, if your system is losing energy to the environment, its modes cannot be complete in the traditional mathematical sense. You cannot decompose the perturbation of the star entirely in terms of simple oscillating modes because some of the energy isn't oscillating. It is simply leaving the system forever.
You have leftover ingredients that didn't make it into the cake.
Yes. This problem, the leaking radiation combined with the extreme relativistic speeds in warp spacetime, was an insurmountable mathematical wall.
Until the breakthrough. Until February 18th, 2026. This is where this story gets incredibly exciting, because a specific team of physicists decided to approach this impossible wall from a completely different angle.
A very clever approach.
We are talking about researchers from the University of Illinois Urbana-Champaign, the University of California, Santa Barbara, Montana State University, and the Tata Institute of Fundamental Research in India. They looked at this tangled, nonlinear mess of relativistic equations. They looked at the leaking bucket, and they realized they needed a radical shift in perspective.
They realized that trying to calculate the complex gravitational interactions of both stars simultaneously across continuously warped spacetime while accounting for radiation was a dead end.
The math was just too chaotic.
Far too chaotic. So they broke the problem down. Instead of modeling the entire binary system at once, they focused their mathematical lens entirely on one star.
Just one.
Just one. They essentially isolated it and treated the partner star purely as an external tidal source. They didn't calculate the partner as a fully realized complex object. They just treated it as a background field of gravity pushing on their primary target.
They simplified the board to focus on the key player.
Yes.
And to do this, they utilized a formidable mathematical tool called the linearized Einstein-Euler equations.
Which is a mouthful.
It is a mouthful, but basically the Einstein part handles the gravity and warp space-time, and the Euler part handles the fluid dynamics of the star's interior. But what does linearized mean in this context?
It essentially means taking an infinitely complex, nonlinear curve and zooming in so incredibly close that locally it looks like a straight line.
Ah, okay.
They made the impossible math merely extraordinarily difficult. But even by isolating one star and linearizing the equations, they still had the problem of gravity changing drastically from the dense core to the empty space millions of miles away.
Right, because the space-time at the surface of the neutron star is monstrously warped, but if you move far enough away, the space-time flattens out, and gravity eventually mimics classical Newtonian physics.
Exactly. So to handle this drastic change in geometry, the team employed a brilliant technique known as matched asymptotic expansion.
Matched asymptotic expansion.
Yes. This is the absolute core of their breakthrough. They divided the space in and around the star into distinct, manageable zones. They defined a strong gravity zone, which encompasses the interior of the star and the severely warped space immediately surrounding its surface.
Okay.
And they defined a weak gravity zone, representing the relatively flat space far away from the star.
Okay, here's where it gets really interesting, because this reminds me of the classic problem of trying to map a massive, complex coastline. Think about mapping the entire coast of California.
Okay.
You absolutely cannot use the same tool to measure the microscopic shifting grains of sand on the beach that you use to measure the broad movement of the tectonic plates from a satellite in space.
The scales are just entirely incompatible.
Exactly. If you try to build one tool to do both, it will fail at both. So you measure the sand grains with a microscope, that is your strong gravity zone, the intricate, intense details near the star.
Right.
Then you measure the tectonic plates from space using radar, that is your weak gravity zone, the broad, distant effects. You solve the math for the beach, and you solve the math for the continent completely separately.
What's fascinating here is exactly how they handled the transition between the beach and the continent. The researchers solved the complex relativistic equations in the strong gravity zone. Separately, they solve the equations in the weak gravity zone, where things are much simpler.
And then they just push them together.
Well, they created an intermediate buffer zone where the two maps overlap. How do you stitch them together? You take the mathematical limit of the strong zone solution as you move outward, and you take the limit of the weak zone solution as you move inward.
And they meet in the middle.
By forcing those two mathematical limits to algebraically match perfectly within that buffer zone, they were able to stitch the maps together. They created a single, uniform mathematical understanding that holds true across all scales, from the ultra-dense core all the way out into the distant cosmos.
But wait, let's go back to the pushback from earlier. What about the leaking bucket?
The radiation.
Yeah. Slicing up space-time into these neat little zones is great for mapping, but the system is still actively losing energy to gravitational waves. How did drawing an artificial boundary line solve the fundamental problem with the radiation, ruining the completeness of the mathematical modes?
That is the true genius of their near-zone decomposition. Remember, gravitational waves are ripples that propagate outward. The energy loss, the actual radiation escaping the system forever, is a phenomenon that primarily affects the weak gravity zone.
The space far away from the star?
Right, the far zone, where the waves carry the energy off to infinity. By structuring their math this way, separating the near zone from the far zone, they are able to physically isolate the tidal field interacting with the star from the radiation permanently leaving the system.
Oh.
Heygate explained that by restricting their primary analysis of the star's internal response strictly to the near zone, they transformed the problem. In the near zone, the system acts almost like a temporary closed loop.
Because the permanent loss of energy only happens once the waves cross the boundary into the far zone.
Exactly.
So by focusing on the near zone, they could calculate the exact quantifiable amount of energy flux crossing that boundary line. They could mathematically capture the radiation, put a precise number on it, and then explicitly subtract it out of the equations for the star's internal modes.
They patched the leaking bucket by turning the leak into a known subtractable integer.
That is brilliant. They accounted for the radiation perfectly by treating it not as a fundamental destruction of the math, but as a tiny subtractable correction to the near-zone physics.
And once they did that, once they stabilized the bucket, they made a massive internal discovery. By manipulating these linearized Einstein-Euler equations, they proved that the tidal field pushing and pulling on the star from the outside acts as a direct driving force of the internal oscillations.
And this led to a crucial condition they had to meet to prove the theory, the condition of smoothness.
Yes, smoothness. They discovered that the math only collapses perfectly into a complete set under a specific condition. They found that as long as the tidal field varying across the star is smooth, meaning the gravitational pull changes gradually without any sudden impossible jumps, sharp corners, or infinite spikes in the geometry, Einstein's insanely complex relativistic equations suddenly behave.
Really?
Yes. Under the condition of smoothness, the relativistic math spits out the exact same beautifully simple harmonic oscillator modes as Newtonian theory.
That is the victory. That is the moment of sheer mathematical elegance.
It really is beautiful.
They proved that even in the extreme, mind-bending reality of general relativity, surrounded by intensely warped spacetime and traveling at massive speeds, a neutron star's internal modes do form a complete mathematical set.
We don't have to invent an entirely new, alien framework of mathematics to describe these vibrations. We can use the damped harmonic oscillators.
The Newtonian springs. We finally have the exact mathematical translation manual. We know how to take the chaotic, relativistic, gravitational ringtones detected by our instruments and flawlessly translate them back into the precise physical vibrations happening inside the star.
It is a monumental theoretical achievement. For years, we knew these stars were ringing out in the dark, but we didn't know if the mathematical language even existed to translate the sound into a physical, structural blueprint of the core.
But this team proved that the language exists, and they wrote the dictionary.
They absolutely did.
Okay, so we have the manual, we know how to read the language of the stars, we have successfully mapped the beach and the continent and patched the leaking bucket. We have solved the brutally hard part. So what are they telling us right now? What is the core made of? Do we have our hard candy quark gluon plasma? Have we found the primordial universe inside these dead stars?
This is where we hit the immediate reality check. The theoretical physics has taken a massive leap forward, but our observational technology is currently lagging behind.
Of course.
As Professor Yunes pointed out, we simply cannot read the core just yet. The most famous observation of a binary neutron star merger was made by the LIGO collaboration in 2017, an incredible event designated GW170817 that forever changed multi-messenger astronomy. But the signal-to-noise ratio from that event just isn't large enough.
The signal-to-noise ratio, meaning the actual clarity of the signal compared to the background static of the universe and the quantum noise inherent in our own instrument.
Yes, the signal is just too faint and the static is too loud.
So we can't make out the ringtone.
Exactly. The subtle imprints of the internal modes on the gravitational waves are deeply buried in the noise. Furthermore, the most crucial information about the neutron star's internal oscillation, The really detailed, high-frequency ringtones that would definitively expose a sloshy quark core versus a rigid neutron lattice occur at very high frequencies.
And our current generation of gravitational wave detectors simply aren't sensitive enough to clearly capture those sufficiently high frequencies.
The math is ready. The translation manual is printed and sitting on the desk. But the microphone we are using to record the cosmos is not yet powerful enough to hear the whisper clearly.
Because at those high frequencies, the physical quantum uncertainty of the laser photons inside the LIGO detectors actually starts to drown out the physical stretching of space-time.
It's a physical limitation of our current mirrors and lasers.
So what do we need? We need better ears. We are waiting on the newer generations of gravitational wave detectors that are slated to come online in the next few years and decades.
Detectors like Cosmic Explorer or the Einstein telescope, which will have vastly improved sensitivity at high frequencies.
And honestly, we also need a bit of cosmic luck. We need to catch a nearby binary neutron star merger event. The closer the merger is to Earth, the louder the signal, and the higher the signal-to-noise ratio.
This raises an important question about what we are ultimately waiting to confirm once those new detectors turn on and we capture a pristine signal.
What are we looking for?
The physics community is waiting with bated breath to see if the equations of state at supernuclear densities, the extreme pressures of the inner core, actually reveal that quark gluon plasma. Is there really a quark core, as some highly debated recent papers have claimed?
Or is it something else entirely?
Right. Are there completely unknown phase transitions occurring inside that we haven't even theorized yet? The data will eventually tell us, and because of this breakthrough, we finally have the tools to interpret that data.
But the theoretical work isn't entirely finished either, is it? The team's current framework, as brilliant as it is, has some constraints that need to be ironed out.
Yes, science is never fully finished.
Right now, the math is perfectly tuned for non-rotating stars. But in reality, the universe is dynamic. Almost all neutron stars rotate, and some of them, millisecond pulsars, rotate incredibly fast, hundreds of times a second.
Incorporating fast rotation into this matched asymptotic expansion framework is the next major theoretical hurdle.
Yeah.
Rotation introduces centrifugal forces and an effect called frame dragging.
Frame dragging.
Yes, where the star's immense mass and spin literally drag the fabric of space-time around with it like a spoon stirring honey.
Oh, wow.
That adds another layer of profound complexity to the tidal responses. Furthermore, the team plans to expand their analysis to include nonlinear tidal forces, which become incredibly significant in the absolute final milliseconds before the stars physically collide.
And what about magnetic fields? I mean, neutron stars possess the strongest magnetic fields in the universe.
Yes, magnetars can have fields trillions of times stronger than Earth's, and those fields undeniably influence the behavior of the internal matter. They will have to account for that eventually.
But as Hegade noted, they aren't starting from scratch anymore. The hardest part, wrestling the core, nonlinear equations of general relativity into submission, successfully slicing up space-time, and mathematically proving that the modes form a complete set, is solved.
They have conquered the mountain of gravity.
Now, it is a matter of adding the realistic configurations, the spin, the magnetism, the nonlinear tides, to an already solid foundation. It is awe-inspiring to reflect on the fact that the math is just sitting there, waiting.
Human ingenuity has outpaced our earthly technology.
We have figured out how to listen to the dense, primordial heart of extreme matter. We are just waiting for our machines to catch up to the sheer scale of the cosmos.
It is a profound state of affairs. We have transitioned from being completely blind to the interior of these extreme objects to having a precise, mathematically proven blueprint of how to observe them.
We are no longer guessing.
Exactly. We are preparing. The structural foundation of how we will conduct extreme astrophysics for the next century has been laid down.
We started this journey looking at an enigma. A dead star so dense it breaks atoms, holding secrets that date back to the first few microseconds of the Big Bang.
Right.
We saw how Earth-bound laboratories fall short, unable to replicate the crushing density without adding blinding heat, and how the universe itself provides the only stage violent enough to test these extremes.
A natural laboratory.
We learned that as these stars spiral toward their doom, they pull on each other, ringing like cosmic bells and sending those vibrations out into the fabric of space. We faced the nightmare of Einstein's math, the leaking bucket of radiation, and the warped geometry of spacetime that made translating those ringtones seem completely impossible.
An impossible wall.
And we saw how a team of physicists sliced up spacetime itself, separated the near zone from the far zone, subtracted the radiation, and finally proved that the language of these stars can be mathematically understood using classical modes. The translation manual is written.
It's an incredible story.
Consider for a moment how the very fabric of space is acting as a literal cosmic instrument. The neutron stars are the massive bells. The immense gravity of their partner is the hammer striking the metal. And the geometry of space-time itself is the air carrying the song across millions of light years to Earth. If human minds have just learned how to meticulously decipher the acoustics of a dead star from the invisible ripples of gravity, what other unseen ancient music is playing in the dark of the universe right now, just waiting for us to build the right ears to finally hear it?